Okay, today we are on page 40. And we're taking a look at number 26. We want to draw representations of helium atoms at two different temperatures. So I'm assuming that what they want us to do is to draw like a little box with some helium atoms in it and another little box with some helium atoms in it. And the two different temperatures, what were they? They were 100 and 500, I think. Yeah, okay. 100 degrees and 500 degrees Celsius. And here's our little helium atoms. There we are. 1, 2, 3. How could you represent the speeds of the two different atoms in the two different containers? Arrows, absolutely. So which one should have the longer arrows? The one that's faster. Should they all be the same size? No. So we'll have longer arrows here, but not all arrows will be the same length. And then over on our left, the slower ones would have shorter arrows in general. But also different lengths. Excellent. Let's represent two different noble gases at the same temperature. We are on page 40. So once again, little box. And let's use, let's just do helium and neon. Now helium is much smaller, so we're going to make those little and teeny. Neon is bigger, so we'll just make them a little bigger. These are at the same temperature. What should our arrows be like? Pardon me? Shorter for neon. Do you guys agree? Yeah, because temperature is essentially the same as the kinetic energy. Yeah, it measures the kinetic energy. So the kinetic energy is the same, but the mass is smaller. And the neon has a larger mass. So that means that the velocity, because kinetic energy is equal to what? Kinetic energy is equal to 1/2 mv squared. And so if our mass is smaller, our velocity has to be bigger in order for the kinetic energy to equal the kinetic energy. So helium has to be moving faster. And the neon needs to be moving slower. All right, very nice. A student is presented with 4 bottles containing different gases. All samples are at the same temperature. Which gas has the fastest particle speed? Yes. Fastest particle speed is helium because helium has the least, she's next door, mass. Which sample has the highest kinetic energy? They should all be the same. My only question is, would it be the 2 moles of CO2 because there's just more mass in general? And I'm not sure. Because my initial instinct is that no, they're all the same. Yeah. And I should have an answer key to this dang thing. And then it'll tell us, and then we'll know. Oh, I do not. Okay, I'm going to have to look that up for you. Okay? So we'll have to figure that out next time. If you have your answer key, you can check it out. It says they're the same. They are all the same. So this is a... Okay, perfect. They're all the same because they all have the same average kinetic energy because temperature is approximately equal to the kinetic energy, which is what I thought at first, and then I confused myself. So sorry about that. Confused myself and then maybe confused you. And we are done with that one. And I'm not going to do 13.3b with you. I will leave that for you to do because it's just more of the same. You can use it as review. Okay. All right, and now we're going into reactions. That's exciting. So here are some reactions that are not in the typical class. You know, decomposition up until this point, decomp has meant that we have AB goes to A plus B. Yes? However, you could probably recognize that these reactions are all decomposition, even though you might not be able to predict the products at this point. Is that correct? Hi. I'm good. I'm teaching though. Because it's AP. Well, sorry. Okay. Yeah, I know. Oh, this should not have an H in it. This is a mistake. Okay, that should just have a CO3. So it's not bicarbonate? It's not bicarbonate. It should just be carbonate. Okay, so let us take a look at these reactions and let's just predict what we should get for our product. So take a look at that. See if you can predict what the product should be. Sorry? XO, yes, plus CO2, because we know that X has to be 2 plus because it's paired with CO3 2 minus, and whenever you heat a carbonate, it will break down into the oxide and carbon dioxide. It's actually pretty straightforward. It is a reaction that you should become aware of and able to predict the products of. Okay, so this is something for you to memorize. Yay! So carbonate salts decompose into the metal oxide plus carbon dioxide. So could you complete and balance those three reactions? Is that what you guys got? Yeah? So they're not too hard to balance, right? They're just kind of like, oh, I needed a 3 there. Yay. All right. Wow. Now we're getting into our bicarbonates. So these were our carbonates. Now we're going into our bicarbonates. And you can heat them. And upon heating, you will end up with, well, let's see if we can predict what XCO3 solid will become. Oh, this one should say XHCO3. What is wrong with me? HCO3. Fix. What does XHCO3 become? Hi. What can I do for you? Okay, feel free to look around. Yeah. I haven't seen it, but yeah.
Thank you.
You're welcome.
Wait. So if you're heating the bicarbonate and then you get a carbonate.
If you continue to heat it, you will then get the oxide and the CO2. Yeah, yeah. But for now, we're just going to say this is what we get, okay? Yeah. So what would we get as our product? We only have one X with an HCO3. HCO3 is -1. That means that X is just positive. Who would X get together with? CO3. So instead of just having XHCO3, we will have X2CO3. We can worry about the balancing later, okay? Plus, and then what are our other two products? CO2 and H2O, CO2 plus H2O. That was pretty straightforward, yeah? So now what we have is, I'm going to get rid of these little pluses and minuses because they're just going to confuse me. And we need 2 XHCO3s. And that's nice because water has H2O. That gives us 2 XHCO3, 2 H's, 2 H's. We need 2 carbons. Oh no, we have 2 carbons. And I think that's it. Yeah? Yeah, that's it. So all bicarbonate salts, also known as metal bicarbonates, decompose into the metal carbonate. Carbon dioxide. And water.
Oh, steam.
Yeah. Well, because you're heating it, right? If you were to put water liquid, it would be okay. No one's going to get too mad at you, okay? Complete and balance the following reactions. Give those a go. Oops. Two of those, that gives us 6 of those. 2 of those. 2. Okay. You guys can tell me if I got it right or not.
How are you finished already?
What do you mean, how did I finish already? I don't know if I actually balanced them. So all I did was I was like, okay, manganese has a +3 charge. So I wrote out all my carbonates. And then I just wrote out all my CO2s and all my H2Os. And then I just hoped for the best in terms of balancing. I was like, this looks good, which is why I'm now asking you guys, did I do it right?
Oh.
Although my carbons don't look good in the first one.
Oh.
Hang on, I'll fix that. I got 3 times 2 is 6. Let's do that. 9 times 2 is 18. That's 12. I don't know, the balancing on the first one's kicking my ass. So if you're like, how did you do it so fast? It's because I did it wrong, Tony. I did it wrong. The other ones are okay, though. I don't think you're ever going to have a question like this. Like, no one's ever going to give you one like that. Do you know what I mean? Like, I just don't think they are. Oh, 2 manganese, 6 hydrogen. Oh, now I need how many hydrogens? I need 3 times 2 is 6 hydrogens. Oh, that's 6 hydrogens. Okay. I need 2 times 3 is 6 carbons. Anyway, let's not worry about it too much because I don't think it's ever going to come up. Is the bottom one not correct? That's totally possible.
Is you have 2 in the front, that means you have 6 oxygen in the total.
Yeah. Okay, so the bottom one. Okay, so we like this one, right? That one's easy? Yes.
The first one is just 3 CO2. First one I think is just 3 CO2.
But I've got 6.
So it's 6 O plus 3 O. It's 9. And then the first one is 3 times 3 is 9. 2 times 2 times 3 is 6. Yeah, it should be 3, not 6.
It should be what?
It should be 3, not 6.
3 carbons?
Yeah, 3 carbons.
But we have a 2 here because we have a 2 here.
Would Manu Hadari come to the office? Manu Hadari.
Should we not worry about the balancing? I don't think it's ever going to come up. I mean, if you want to take it home and worry over it, you can do that, but I don't think it's worth your time. Are we good with that?
It is 6 carbons, so it's...
Okay, I'm moving on. I don't know about the rest of you. Acids, carbonates, and bicarbonates. Quite frankly, I think you're more likely to come across this one. I think you're more likely to come across the decomposition of a carbonate than a bicarbonate. I think if they were to give you a bicarbonate, they would probably give you like the 2+ ions, so the balancing is really easy. Do you know what I mean? Okay, so acids, carbonates, and bicarbonates. So let's take an acid, and then we'll put it with a carbonate, and then we're going to take an acid and put it with a bicarbonate. Ms. Chatrath is in the room next door.
Also, we're just skipping all the other ones.
What do you mean all the other ones? There were other ones?
There's like chlorate.
Oh, there are. Okay. Chlorates.
So are we doing this or...
Oh, let's do the chlorates. The chlorates are fairly straightforward. Okay, so you have a chlorate, and based on how our carbonates worked, it's kind of the same. Well, it's not really. So we have something ClO3. What should we get as our product? Metal chloride plus oxygen. Okay, so XCl plus O2. So metal chlorates decompose into metal chloride plus oxygen. So LiClO3, you can predict those, balance them. All right, we're out of time. I would personally balance this last one by doing halves, right? Because that would just make my life easier because I've got the amount of chlorines I want. I've got the amount of irons I want. So if I want to have 9 oxygens, I can say 9 halves of O2. Then I multiply everything by 2 and my coefficients end up being 2, 2, and 9. That's just a reminder of how you can use halves. For homework this week, let's just have you do pages, not very much, it's just like 41 and 42. Okie dokie. Excellent.